Okay, now, welcome to Unit 5, Lesson 13, Exponential Functions with Base E. Let's look at situations that can be modeled using exponential functions with base E. E is an irrational number. So on the calculator, sorry about that, it's approximately 2.7183 if we round to 4 decimal places. If you round to 3, it's 2.718. If you round to 2, it's 2.72. But you're not going to use that. That is not that accurate. This is a little bit more accurate, but the top one is usually best. This is probably the most common. Is to round to 3 decimal places. But the delta math will most times ask you to round to this one. So I'll write delta math here. Okay, so now what we have to do, how do we put E into the calculator? The E is next to the 4 button. So let's show you how to put A into the calculator. You're going to type 10. Then you have to hit the second button. And then next to the 4 is a button called ln. That's the natural log. That's the opposite of E. You put that in, and then you get E with a square, and then you put 1.1, and then you hit enter. Hit these buttons. And then do the same thing for the next ones. For B, use parentheses, and C, do the same thing. Make sure for C, you can hit second, ln, that's going to bring up E. You're going to put 9 divided by 23. Make sure you hit the right arrow. The direction arrow buttons, well, they're actually shaped like that. They're not squares. They're kind of like that. So make sure you hit the right direction arrow button and to bring the cursor down, then hit +7. Because if you don't hit the right arrow, it's going to be 9 over 23 plus 7, and you're not going to get 8.47891. And the book seems to be rounding to 5 decimal places. Remember, these numbers are irrational. They never repeat. They never end. Okay, so what I did was put these numbers in. I actually put the equations in, and then I looked at my colony of insects. And here's the population. And remember, these are in thousands, so you have to multiply these numbers by the thousands. And what you can see by looking at the table is that E grows slightly faster than the regular function that approximates E. So E is better to use in a lot of modeling because it is a little higher than just regular numbers without doing it. And here's the growth rate, 0.02. Here's the growth rate, 0.02. So you don't have to add 1 to it. You just put in whatever the growth rate is, unlike what you had to think about with regular exponential functions. All right, so question 2. The populations are very close, but the E model grows slightly faster. So for 3, here's some equations. We're going to graph all of these in class. All right, so now to change the window, you have to hit the window button. The window button is the gray buttons at the top, and it's above second. It's above mode, actually. It's right above mode. Hit the window button. Your X max will come up first. So put that as +50. X min at 0. And Y max and min at +80 and 0. So when we turn it on, we hit window. X min is the minimum, so 0, then 50. Leave X SEL, X scale alone. And change Y min and Y max to 0 and 80. And then graph all 4 of them, and then you'll see. And we're going to do this in class. And you'll see the E ones grow slightly faster. Okay, now here how E is used. This is what the numbers are. Remember, 13 is your start. E is a constant. The growth rate, all you got to do is transform it into a number. You don't have to add 1 or subtract 1 to it. That's your growth rate. And T is time, usually time, or the number of growths. But usually it's going to be time. All right, so we're going to read that. Here are some situations in which a percent change is considered to be happening continuously. For each function, complete any missing parts of the function and identify the growth rate as a percentage if it is not given. All right, so at time t equals 0 measured in hours, the scientist puts 50 bacteria into a gel on a dish. The bacteria are growing and the population is expected to show exponential growth. Here's our function. What is the continuous growth rate? You take the 0.25, you multiply by 100, and this is 25%. Now, what E actually is continuous growth. So, if I was to write this without a E, I would write 1.25 because it's 25% to the T. This is not continuous growth. This is discrete growth. What does that mean? That means at every interval. So let's say my interval is 1, 2, 3, 4, 5. And this is something we did in sequences. It grows at every step. It does not grow in between each step. This is called discrete. And that's this one. Now, continuous growth it doesn't matter what my intervals are, it constantly grows in between intervals. So that's the difference between discrete and continuous. One constantly is growing and one only grows at certain intervals. It doesn't do anything between the intervals. Okay, so for 2, my start was in 1964 was 192 million. 192 is my start. I take 1.4%. I divide it by 100 to get a number, and that gives me 12.014. And then for my final one, 1955, we were at 2.5 billion. The continuous growth was 0.0168. I multiplied by 100 to get a percent, which gives me 1.68% per year. Okay, so we're going to put this into the calculator. For number 1, use graphing technology. Well, we're not going to graph it. We're going to put this in the y equals. We're going to hit 50 second ln, 0.25x. You can't use t in the calculator. You got to use x, t, theta, n. And then we're going to hit second graph to read the table of values. We're going to go down to when x is 50. Or I could just change the table start to 50 if I want it. And so this one was about a little bit over 600. It's a little bit over 600 bacteria. It's almost 610. So let's put that down. You can't have point something bacteria, so we'll use 609. We'll round it off to a whole number. About how many hours does it take for the dish to double? Okay, so how long does it take to go from 50 to 100? But a little less than 3 hours. So less than 3 hours. X is less than 3 hours. So let's not use X, let's use time. Time is less than 3 hours. Okay, again, put this into y equals, clear out what's in y equals, put this one in. Okay, we don't need to graph it. We're just going to hit second graph. And then the equation models the population in millions after 1964. What does the model predict in 1974? What does T stand for? T is 1 year. So we're going to scroll down to 10 and 220 mil. Because the population is a million, so they left off those 6 zeros, and we're just dealing with that part of it. And which year does the model predict? 300 million, and we're going to scroll down. So when X is 32, which is what? 1964 plus 32 is 1996. The population, so X equals that. We had to add it to the original, which was our 0. So 32 from our 0. X equals 0 was 1964. So X equals 32 is 1996. The Y is going to it's going to approximate a little over 300 million. Down here, because this is hundreds of, in millions, this is 300 million. So I'm going to go over to the right and give you the actual numbers. So 300 million, and I need 6 more numbers after this. 514. So what I did was go down to 32. I right arrowed over into the Y1 column, and then at the bottom, I get the numbers. And I'm going to round this up. This is 514309. The number next to the 9 is a 5, so I'm going to say 310. So in 1996, bottom model, we should have had approximately that many people in the United States.